So next topic for indeterminate forms is going to be the indeterminate product. An indeterminate product is something where you attempt to use the direct substitution property and you wind up with 0 times either positive infinity or negative infinity. An example of an indeterminate product would be something like the limit as x goes to 0 from the right hand side of x times the natural log of x. If you attempt to use the direct substitution property with this, then as x goes to 0, x is going to go to 0, and as the natural log of x, as x goes to 0, the natural log of x would go toward negative infinity. Natural log of x has that nice little vertical asymptote right as you're getting close to x equals 0. As a result, this will be considered an indeterminate product. To evaluate an indeterminate product, it is necessary for us to do a little bit of algebra. The technique that we're going to use is referred to as force a fraction. In order to force a fraction, basically is saying when you have two things that are multiplied together, like you do for an indeterminate product. Our goal is to be able to use L'Hopital's rule, but to use L'Hopital's rule, it'll be necessary for us to make sure that we have a fraction in there. The way that we can force a fraction is saying that multiplying by something is the same thing as saying divide by the reciprocal of something. I realize this seems like the kind of thing that you would want to fix right away as soon as you see it, but when it's in the form of a quotient, we are guaranteed that one of these is going to be 0 divided by 0, and the other one is going to be infinity divided by infinity. Once it's in one of these two forms, we can then apply L'Hopital's rule, and everything should go quite nicely. So just to give a demonstration on how that would work for our previous example, there are actually two different ways that we can force a fraction with this. The ways are, I could force the x into the denominator by calling this the natural log of x divided by 1 over x. In this form, if I were to allow x to go to 0 using the direct substitution property, this would now take the form negative infinity divided by positive infinity. Whereas if I were to try it the other way and take the limit as x goes to 0 from the right, I could also force the natural log of x into the denominator by calling this x divided by 1 over the natural log of x. In this form, if I were to try to use the direct substitution property, I would get a 0 on top and I would get a 0 on the bottom. So once again, this forces a fraction. Now taking a look at these two forms though, you should pose the question, which one of these seems like the more natural thing to try to differentiate the top and bottom? Well, we can differentiate the natural log of x without too much difficulty. 1 over x could be expressed using the power rule, x to the negative 1, so neither of those derivatives would be too bad. For this one though, derivative of x, that's about the easiest problem I could ask you. Derivative of 1 over the natural log of x seems horrible, terrible, light it on fire. Absolutely don't do it. That one, absolutely don't. Instead, what we'll do is we will then take the limit as x goes to 0 from the right, and we'll apply L'Hopital's rule. L'Hopital's rule says differentiate the top. Derivative of natural log of x becomes 1 over x, and the derivative of 1 over x, what we're going to do is think to ourselves 1 over x is the same as saying x raised to the negative 1 power. Differentiating this, according to the power rule, would be negative x to the negative 2. Now, simplifying this with algebra means that we have 1 over x over negative 1 over x squared. Much as it pains me to say this without an audience reaction, yo dog, I heard you like fractions, so I put fractions in yo fractions. Now we are dividing one fraction by another fraction, so rather than using L'Hopital's rule again, what I'm going to do is just do algebra. This is the same as saying 1 over x times the reciprocal of negative 1 over x squared. That would be negative x squared over 1. By performing that algebraic manipulation, I can proceed to continue to simplify. X squared over x simplifies to x, and the negative sticks around. At this point, I can make use of the direct substitution property, and the direct substitution property says that this will be negative 0, also known as just 0 because it's a final answer.